For decades, we've tried to fix sick lakes with what seemed like common sense solutions. But time and again, these fixes have backfired, sometimes making the problem catastrophically worse. Today, we're going to look at why these common restoration methods struggle and why a fundamental shift in our thinking is underway. The most obvious problem in a dying lake is the lack of oxygen at the bottom, a condition known as hypoxia. The logical solution, then, would seem to be aeration, pumping air into the water. But it's not that simple. Most aeration devices blow bubbles through the water that only manage to raise dissolved oxygen levels near the surface. This actually amplifies the difference in dissolved oxygen level between the top and the bottom, supercharging the surface layer while leaving the depths to stagnate. Many systems create so much turbulence that they do more harm than good. This leads to a cascade of unintended consequences. First, many of these aeration systems provide inconsistent oxygen levels. One day the oxygen is up, the next it's down. This fluctuation creates an unstable environment where only the most opportunistic organisms can thrive. And the undisputed champions of chaos are cyanobacteria, the microbes responsible for toxic blue-green algae blooms. They are agile and adapt quickly to changing conditions. The beneficial species of algae simply can't keep up. They get outcompeted and the lake shifts further toward a toxic state. Second, that turbulence can be devastating. Many aeration designs stir up the lake bed and decades of sunken organic matter, all rich in nutrients. When you blast it with turbulence, you're resuspending all of that material. Organic matter gets lifted off the bottom, and with it, a massive pulse of nutrients, especially phosphorus, is stirred back into the water. As it moves further away from the diffuser, it gradually settles back into the sediment to decompose and deplete oxygen once again. This causes pulsing and variations in oxygen levels and internal nutrient loading, which plays into the hands of cyanobacteria. There was a widely reported case in Vermont where a $1 million aeration system had to be removed because it was making toxic algae blooms worse, not better. It was actively feeding the very problem it was meant to solve. To avoid this, some designs try a different approach. They installed diffusers on a mini platform, raising them several inches above the lake bed. The idea is to aerate the water without stirring the sediment. But this creates a new problem. It leaves a persistent, stagnant, low oxygen zone right at the most critical interface, where the water meets the sediment. And it's from this hypoxic layer that nutrients, especially phosphorus, constantly leak upwards, providing a slow, steady drip of fuel for algae. Other attempts have focused on floating circulators that move the top layer of water around, hoping to push oxygen down. But they simply can't. The physical properties of water, especially when it's stratified into temperature layers, prevent this surface motion from reaching the depths. The deep zones remain stagnant, starved of oxygen, and continue to leak nutrients. Now, there are highly specialized engineered systems called hypolimnetic oxygenators that can add oxygen to the deep water without disrupting the lake's natural temperature layers. But these systems are incredibly expensive to build and operate. They often only treat a very limited area of a large lake and require constant, demanding maintenance. They're a viable option for certain large reservoirs with massive budgets, but for the vast majority of the world's lakes, they're just not a practical solution. So if mechanically adding oxygen is fraught with problems, what about a more direct approach? What about just killing the algae? This brings us to the second major category of traditional lake treatments: chemical algaecides and herbicides. These are often seen as a quick fix. You see a bloom, you spray it, the bloom disappears. But the ecological trade-offs are immense. The first issue is that these chemicals are indiscriminate. They're like a broad-spectrum poison that kills all phytoplankton, not just the harmful cyanobacteria. So they also wipe out the beneficial algae that are a crucial food source for zooplankton, the tiny creatures that feed fish and form the base of a healthy aquatic food web. The second and perhaps more critical issue is what happens after the bloom is killed. All of that dead algae biomass, tons of it, sinks to the bottom. As it decomposes, the bacteria doing the work consume enormous amounts of oxygen, dramatically expanding the lake's hypoxic zones. This decomposition also releases all the nutrients that were locked up in the algae right back into the water. In other words, killing the bloom directly fuels the next one. It's a perfect feedback loop of decline. Third, because cyanobacteria thrive in the exact low oxygen, high nutrient conditions that are created after a chemical treatment, they rebound much faster than the beneficial species. Each time a lake is treated, the ecosystem is pushed further and further towards cyanobacteria dominance. The treatments inadvertently create the ideal conditions for the very organism they are meant to control. Finally, many of the most common algaecides are copper-based, and copper does not disappear. It's a heavy metal. When it's applied to a lake, it eventually sinks into the sediment, where it accumulates. Over years of treatment, copper levels can become so high that they pose a major problem for any future restoration work. For example, if the lake ever needs to be dredged to remove excess sediment, the dredged material could be classified as contaminated waste due to the high metal concentration, making disposal prohibitively expensive or even prohibited altogether. This brings us to our third class of intervention, phosphorus precipitants. If nutrients are the problem, why not just lock them away? That's the idea behind chemicals like aluminum sulfate or alum and activated clay. When applied to a lake, they bind with phosphorus in the water column and drop it to the bottom, locking it into the sediment. The intention is to trap the nutrients permanently. But here's the catch. That chemical bond is often temporary, and its strength depends entirely on oxygen. When the sediment at the bottom of the lake becomes hypoxic, which, as we've seen, is the core problem in most struggling lakes, a series of chemical reactions mediated by microbes can break those bonds. The phosphorus becomes soluble again and rises back into the water column. This process, known as phosphorus remobilization, means the nutrient trap fails exactly when it's needed most. The permanent solution becomes a temporary patch that is undone by the lake's underlying sickness. And just like with copper algaecides, aluminum-based treatments add metals to the sediment. Over time, repeated alum treatments deposit significant amounts of aluminum. This, too, can create metal-enriched sediment that complicates or prohibits future dredging. When you step back and look at the pattern across these different methods, a clear picture emerges. For decades, we have been tackling the symptoms, the visible algae blooms, while failing to address the root causes hidden in the deep water chemistry and the sediment. In fact, many of our solutions have unintentionally worsened the deep water hypoxia, increased nutrient recycling, and pushed lakes closer to a state of permanent cyanobacteria dominance. This widespread failure has led to a major shift in thinking. Government agencies and international scientific organizations are now calling for a new paradigm, nature-based, ecosystem-supported methods to restore our lakes, rivers, and reservoirs. The focus is shifting away from short-term fixes that disrupt ecosystems and toward restoring the natural processes that make them stable and resilient in the first place. So let's summarize what we've learned. First, restoring deep water oxygen is incredibly challenging, and most conventional aeration and circulation systems come with unintended negative side effects. Second, chemical treatments like algaecides kill indiscriminately, but their decomposition worsens hypoxia, recycles nutrients, and leaves a legacy of metal residues in the sediment. Third, phosphorus precipitants, which promise to lock away nutrients, often fail under the low oxygen conditions they are meant to treat. The conclusion is clear. The old methods of waging war on symptoms have provided temporary relief at the cost of long-term decline. Many of our lakes don't need another dose of chemicals or a more powerful mixer. They need new strategies grounded in nature, biology, and ecology that work to restore the fundamental processes of a healthy system. The future of restoring our vital freshwater resources lies not in fighting nature, but in learning how to help it heal itself.
We've learned how to measure the problem and how to implement solutions. But to truly understand the life of a lake, we have to step back and look at the big picture. Join us for our final video, Lesson 10, The Lake Death Spiral, where we synthesize everything we've learned into a single, cohesive story of lake life and death. To go to the next lesson, use the link below. And don't forget to like and share, and subscribe, so you'll get notified when the Lake Science 102 series is uploaded.